So let us go live. Hello, and once again, welcome for the last time in this 15 days physical science program for class 10. It has been a wonderful journey for me, even if the number of participants is small, but if you are a performer, supposing you are a performer, whether you are performing a fine art, like painting, like acting, or a dancing, or a singing, it is always better to have at least one person who will be watching you with heart and mind, giving you 100%, than having a hall full, hundreds of viewers, participants in the gallery, in the hall, who are disgruntled, who are just watching under duress, under compulsion they are watching, but they are not interested. I said disgruntled audience. Hundreds of disgruntled audience is far worse than only one passionate and interested participant. So that I always cherish, even if our programs are meant for good students who have a scientific background, and have the interest to study science, they only can benefit from our program. Rajasri, welcome. So we will take up from where we left last time. Let me tell you that very soon you'll be getting a notification both in our website and in the WhatsApp group that we might be having a test, the final level test, on which the merit list will be prepared, and the date will be June 25th, tentatively, unless otherwise we have gross difficulties to change the date or to cancel the program entirely. But as long as you don't find any notification, you stay tuned to get it. And in that, we will have the chapter optics, reflection from spherical mirrors, concave and convex, and reflection and refraction in the spherical lenses, the convex and concave. These are part of your optics program. Of course, the functioning of the eye, so that I am excluding for the test. That is, of course, there in your program, in your course, but we will be excluding that. So you can find out those videos if you do not have any access to any tutor or any person who will teach you that. You can open the playlist and find the chapter. It will be a separate chapter, separate playlist. We'll find reflection and refraction of light. You'll get all those, just like we are having this program. Maybe in some previous years, we had the program on optics. And that has been recorded and it is stored in the YouTube. You can watch. Now let me share my screen. Stop annotation. And let me I hope you have just found some time to revise what we did to write the electronic configuration on the basis of SPDF, on the basis of orbitals. Although we are not having the proper and adequate knowledge about orbitals, but still I told you to have this mechanically and learn the periodicity in the basis of electronic configuration. Who have tried to write the configuration of a few more elements from the table and saw and seen how many lone pairs and how many unpaired electrons are there in the elements? Rudra has done it. Who else? Who else? Omo has done it. Oh, we can go for 8, but 8 is not yet been used. Very soon it will be used because the new element is about to arrive. I mean, it will be discovered soon. So the 8s will be used in that new element having atomic number 119. So we don't bother about the 8th now. Then I told you, you just try to do it again because many of you have not practiced. Oh, this would be parallel. This would be parallel. If you don't write perfectly, alignment is improper, then you will find the alignment is not good. So today, my alignment is not good. So you are not having parallel lines, little deviation from parallel nature. So the downward arrow mark means you go in this direction from top to bottom. And if you finish one arrow, then go to the top of the other arrow and finish it till end, then go to the next arrow and so on. Now, if I ask you to find the electronic configuration which we didn't do for say potassium 19, can you write down in terms of, and let me ask you that how many maximum electrons are present in the subcell? Obviously your answer will be 2 for S subcell because it has one orbital, and one orbital can accommodate 2 electrons with opposite spin, and P subcell has 3 orbitals, so altogether 6 electrons, D 5 orbitals, 10 electrons, F 7 orbitals, 14 electrons. So this is the maximum limit that you can go, can't cross it. So please write down, I give a minute's time to write down the electronic configuration of potassium in terms of SPDF, and raise your hands. Welcome viewers who are watching directly in the YouTube. So welcome, and many more will join because this morning time is really unsuitable to many. I found that my feeling, my gut says that more than 90% of the population, they do not like morning time. Maybe I'm wrong. Maybe it is 80% or 70%. They always want to enjoy the early morning time in deep sleep. So, yes, one answer has come. Yes, Arjay Kumar Sahu has written correctly in terms of, and so also Rudra. Arjay, you have not raised your hand as like Rudra. So that, oh, this list, participant list, nobody can see. Perhaps only I can see. You cannot see. Okay. So Rudra and Arjya have done. Jyoti Prakash, you have not yet raised your hand. Yes, Jyoti has now raised his hand. Oma, kono sudhala? 1s2, 2s2, 2p6, 6 8 10. Then 2 ra sarigala, 2 ra jodiye. Then 3s2, then 3p6. এটা ହେଇଗଲା କେତେ 6 2 8 2 10 2 12 6 18 ତାପରେ କୁଆଡେ ଯିବ ଗାଡି ଦେଖ ସିଏ ତୀରକୁ ଦେଖ 3p ପରେ କଣ ଆସୁଛି 3d ଯଦିଓ 3 ରେ ତିନିଟା ସବସେଲ ଅଛି spd କିନ୍ତୁ 3p ପରେ ଏନର୍ଜି ୱାଇଜ ଆସୁଛି 4s ତେଣୁ ଏଠି ଆଉ 3d କୁ ଯିବନି 4s ଗୋଟିଏ ଯଦିଓ s ର capacity होची 2 but it will have only one electron. So ସେଥିପାଇଁ ତୁମେ କଣ କରୁଛ ନା जो स्कूल 10th ଭିତରେ ପଢୁଛ କଣ ନା 2881 ଏଠି 9 କରୁନ ଏବେ ଜାଣିଲ ଯେ ନା 8ଟା ଇଲେକ୍ଟ୍ରନ୍ ଫିଲ୍ ଅପ୍ ହେଲା ପରେ ଗୋଟେ ସେଲ୍ ରେ ତାପରେ ନେକ୍ସଟ ସେଲ୍ କୁ ଯିବ next cell re dita puron kala pore puni back karibo back to pavilion if its capacity is 18 then 18 karibo. Sometimes so the number of the fourth cell is the valence cell, and if you draw a small box to find out the number of unpaired electron, you'll find only unpaired electron. Let me abbreviate unpaired electron as UPE and lone pair as LP. So number of unpaired electrons is only 1, and there is no lone pair because you will not count the pairs. All these are pairs as lone pairs. They don't participate in bonding at all. Only one electron will participate in bonding, and that too in ionic bonding because it is a highly electropositive metal. The metal doesn't have a tendency to gain electron and make bonding with others. So it will lose electron easily and it will be forming K+. That is why all these alkali metals, they enjoy only one valency, that is +1. Electrovalency of +1. They lose only 1. No way to dislodge any electron from the penultimate cell, which is enjoying a stable octet configuration. Right? So, in the same manner, if I ask you to find out the electronic configuration of calcium, which is 20, it will be exactly one more. 1s2, 2s2, 2p6, what you wrote. 3s2, 3p6. This is 18, and instead of 4s, you have 4s1, you have 4s2. So the fourth cell is the valence cell, and there is no unpaired electron. But these two electrons will be unpaired and will be lost one after the other. So they will be lost altogether at one time. You can't satiate the desire of calcium to lose only one electron and becomes 1 plus. The moment the first electron goes, the second electron will go simultaneously. So it always, all these alkaline earth metals, calcium, magnesium, strontium, barium, they have to lose 2 electrons. So they have an oxidation state or valency of +2 everywhere. No variable valency shown by group 1 and group 2 alkali and alkaline earth metals. Similarly, when you talk about aluminium, which is 13, or gallium, which is 31, say aluminium, 1s2, 2s2, 2p6, it is 10, and it will be 3s2, 12, and it will be 3p1, 2 plus 2 plus 6, 10, plus 2, 12, plus 1. So if I ask you to tell me how many lone pairs and unpaired electrons are present in aluminium, and all these elements belonging to group 13 or group 3a, starting from boron, aluminium, gallium, indium, thallium, the situation will be exactly similar. The valence cell configuration is exactly similar. So if you draw a box, you will find one lone pair and one unpaired electron. Draw 3 rooms, but 2 rooms are lying vacant. So the unpaired electron is 1, and lone pair is 1. And of course, when bonding comes, then all these 3 electrons will be participating most of the time. Particularly aluminium, boron, all these 3 will be either joining in covalent bonding, sharing, or they will be leaving one by one, like aluminium chloride or metal like aluminium. It shows ionic bond with strong non-metals like chloride, bromide, all this. So all these will be leaving together. So aluminium doesn't have a variable valence. This is +3. But as we study, as you go down the group and come to indium and thallium, particularly the last one, thallium, it will exhibit variable valency. It will exhibit first, this unpaired electron will go, it will show a +1 valency. And also there are compounds where all the 3 will go, like aluminium, boron. Boron doesn't show a ionic bonding, it always shows a covalent bonding, because it is small in size, and we'll study that the ionization energies are very, very high. It's not a metal, it's a metalloid. Study that. Now, so thallium shows variable valency. Similarly, if I ask you to find what is the electronic configuration of tin, which is 50, don't be scared. It is as much easy as for others. Write down. I give you a minute's time to write down, to go up to 50 and show me how the electronic configuration looks like. It belongs to the carbon family, group 14 or 4a, where you will find in the valence cell there will be 4 electrons. One is paired, the other 2 are unpaired. So welcome viewers who are watching from the direct live streaming YouTube video. So you can just put some words in the chat box, hello or whatever like that, so that I will know that you are really watching. Hello there. You can also write hi. What's up? Now, who has written Jyoti Prakash Pal and Rudra? They have finished. So also Arja, not Arya, Arja. Om Prakash. Well, Om, perhaps your schoolmate, batchmate, Miss Shraddha Suman has left for school, and that is why she has not joined today. I'm a bit sure about that. I guess she might be transiting today or have already gone yesterday to join the school. So it's not possible when you are in school. Right? So tell me if I'm wrong. 1s2, 2s2, 2p6. So the second cell is over. First cell is over. Then 3s2, 3p6. But after that, you don't have 3d. You have 4s2 while filling. Then comes 3d10. So the third cell is complete now. Then after that, we have gone up to, 30. This is adding up to 30. Then it comes, if you look to the this principle, Madelung's, this is what we call the Madelung's rule or the Aufbau's principle. After 3D comes 4P, then 5S. 4P, 6. It is 36. Then comes 5S2. It is 38. Then after that comes 4D10. 38, 10, 48. Then comes 5P6. But if you make it 6, then it will be 54. But we want to go to 50. So that we have to make it 2. So that it is 50, 48 plus 2, 50. Now, if you look to the 4 cell, is still not complete. 4F is still waiting. Its turn will come after 6S. Doesn't matter. But we are interested in the valence cell of teen, which is the 5th cell, is the last cell. The last cell is the valence cell. So if we draw a small box here to find a lone pair in the s orbital, and here we have to fill 2 electrons. Who can tell me which rule will be followed when we fill electrons in a set of degenerate orbitals? Just write down or tell me which rule is followed. Miss Rajashree.
Horn rule.
Oh, so Rudra, you will be called Rajashree. Yes, it is the Hund's rule that will be followed. There are 2 electrons, so each of the 2 orbitals will be getting one electron with same spin. And even the third electron, had there been a third electron, it would have gone to this with same spin. Then the 4th electron will be pairing the 1st, 5th, 2nd, 6th, 3rd. So in teen, we have 2 unpaired electrons and 1 lone pair. So with this much of discussion on the electronic configuration, you might be those who have studied in advance, like Jyotiranjan Pal. He might be interested to have a discussion on some anomalies. For example, chromium and copper. Let me tell you, there will be anomaly in the configuration. You can write down as per the rule, but there is a little violation of the Madelung's rule that we studied. So in chromium, you are supposed to write, if you do not know the deviation or anomaly, you will write this. It comes to 24, 4:3D4. But there is another rule to explain the anomaly, that when the D subcell is half filled, or let me say tell you in another way, if the D subcell is one sort of half filled configuration, one sort of full filled configuration, then one electron is transited, promoted, or is transferred, is the right word, from the nearby 4s to the 3D to make it half filled or full filled. So that is the case only with chromium and copper. So since the D subcell has the max capacity of 10 and 5 is the half value, so now in the usual configuration, you find it is one sort of becoming 5. So one electron will join here. So this is a wrong configuration. It will be 4s1 and 3d5. And you will be surprised to know that chromium has 6 unpaired electrons, which has been verified experimentally. You will learn how to verify the number of unpaired electrons from the magnetic moment data that you will study. So there are 5 rooms, one, hund. So altogether, there will be 6 unpaired electrons. And similarly, so this is the correct one. Similarly, copper, it is expected to be, according to Madelong's rule or the Aufbau rule, it is expected to be 4s2, 3d9. But since again it is one sort of becoming full, so one electron will be transferred. So it will be actually 4s1, 3d10. So the unpaired electron is present in the 4s, not in the 3d. 3d is completely full, so there is no need of drawing the D 5 boxes or 5 rooms. Only we want to see the number of unpaired electrons. But that is not present in the D, but present in 4s. So there are several anomalies in the periodic table. When you go to the 11th class, you'll find not only these two, but there are many. Let us now open our copies. If you are watching in the YouTube video, please open your copy. It is better if you have a plain copy and put it in the landscape mode, not in the portrait mode, but in the landscape mode, and draw with your pen. Don't use pencil. Just it should be a what we call a easy hand drawing, or a what is the appropriate word is a free drawing. So there is no need to be conscious that the lines are not horizontal or vertical perfectly. So don't bother, and use the landscape mode, so that you get a lot of space to create 18 groups. So now draw 2 groups in the left, what we call the left portion. Leave a lot of space in between and draw 6 groups. Oh my God! If you're not happy with pen, you can use pencil. Because I have a rubber eraser here, I can do the needful, but you can't. 3, 4, 5, and 6. One, 2, 3, 4, 5, 6. Let me. Right? So this is the left portion. this is the right portion, and this is the middle portion. And then your job is to draw horizontal lines to make 7 periods, 7 horizontal rows. This is 3, 4, 5, 6, and 7. So do the 1, 2, 3, 4, 5, 6. So this space is dedicated to Rajasri Rajalakshmi Sahu. It's not needed. Let us dedicate that space to someone like Rajasri, who is dozing now. Anil sir, good morning to you. And those also who are watching, good morning, Anil sir. So, are you following me? Raise your hands, those who are in Zoom with me, what I'm instructing to you. Have you already drawn the 7 horizontal rows, what we call periods, and 8 vertical columns we have drawn, 2 in the left side and 6 in the right side, and we have kept the middle portion intact. If you have already done, then what you do, write down, this is in the left side, this is period 1, 2, 3, 4, 5, 6, 7. These are the periods. And from the 4th period, you draw 10 columns. It starts from the 4th period, 10. Small, because if you don't have left a good space, then to get 10 columns will be difficult. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, I can get 10 columns. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I need 10 groups to be inserted between the left portion and right portion, to be called as middle portion, to have 10 groups. Done? If you have done, then let us designate the groups. Group 1, group 2, group 3 here, group 3 here, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then come back to the top, 13, 14, 15, 16, 17, and 18. There are 18 groups in the long form. Gone are those days when we were studying, so it was IA, it is written in Roman, 1A, 2A, and this is 3A. I'm writing because old is gold sometimes. 5A, 6A, 7A, and this is group 0. The group 18 was called group 0. These are the A group elements, the left portion and the right portion. The 2 portions are called A group elements, and the middle portion was called the B group element. This is 3B, 3B, 4B, 5B, 6B, 7B, and 8, 9, 10 combinedly group 8, no B, group 8, and this is 1B, this group 11. Nowadays it is called group 11. It was called 1B, and this is 2B. Right? Now let us put the elements in all these as much as possible. Let us put elements now. Let us write hydrogen here and helium here, period wise. The first period has only 2 elements. Hydrogen is the beginning course, it doesn't have a fixed position. It is both in group 1 and group 17. So it is usually written in group 1, although it's not a metal, but it is written in group 1. Then let us write in terms of groups. All other elements to be written in terms of groups. So this is the lithium, the first member of the alkali metal: lithium, sodium, potassium, rubidium, cesium, francium. Quick, be quick. These are called alkali metals. And then beside lithium, write beryllium, then its brother is magnesium, its elder brother is calcium, then strontium, rubidium, radium, calcium, barium, barium, and then radium. You know, francium is radioactive element. You can put a star indicating this is a different type of element which are not stable. Every time it is disintegrating to new element at a particular rate. And these are called radioactive elements. You might be wondering that I have perhaps decided to deliver today's lecture only in the language of English. May it be, you guys are quite smart when you are sustaining up to the 15th day. You are quite smart even to understand in English. I have realized whenever in an Odia medium forum, even in English, even in colleges, I tell you my experience, even in colleges in higher level in Odisha, where most of the students, most of the participants are from Odia background, they will definitely love bilingual. English sometimes, but Odia most of the time. If they're not Odia, non-Odias, then Hindi most of the time. If you speak the entire lecture in English, you are going away from the audience, you are alienated from the audience. It is for sure. The participants, the viewers will not be as much close to you as they would have been had you used some vernacular language or national language. So I understand that, but even then, I deliberately am choosing to speak the whole of the lecture today, the first one and the second one, in the language of English, because I would send you off with a feeling that yes, we can also speak in English as much good as possible. Now, then you jump to group 13, the right portion. This middle portion is called the transition elements. These are the transition elements. I write TM, stands for transition elements, transition metals. And these are also called D block elements because the last electron enters into a D orbital. That is why the entire middle portion is called D block. And these two groups, the last electron enters into a S orbital. So this is called S block. And these 6 groups is called P block. Obviously, the last electron enters into the P orbital. And we shall be drawing very soon 2 rows at the bottom to designate them as lanthanides and actinides, which have no place in the main body of the periodic table because they contain 14 elements each. 14 elements each. This first row is called lanthanides or lanthanones or lanthanoids. So many names are there. This is lanthanoids and this is actinoids. And this starts from 50. I'll tell you just after some time. I will tell about. Then just jump over to the right portion. This is the boron family, starts from boron. There is no element in the first period or in the top. This starts from the second period, every element: boron, aluminium, gallium, indium, thallium, and this one is a newly discovered element, what we call nihonium. So you need not write that, because that is a synthetic element, is a very, very short-lived element, synthetic and radioactive, man-made. So need not bother about nihonium. Now coming to the carbon family, group 4A or 14: carbon, silicon, germanium, tin, lead. Just write down what I'm doing: lead, tin, germanium, silicon, carbon. And flerovium is again similar to nihonium, which is synthetic and very, very short-lived and radioactive. And coming to the nitrogen family, group 15 or 5A: nitrogen, phosphorus, arsenic, antimony, bismuth. And moscovium is similar type. Nothing to worry about it, moscovium. Then called the oxygen family, group 16, 6A: oxygen, sulfur, selenium, tellurium, polonium. And this livermorium is just nothing, but polonium, is radioactive. It's natural. I'll tell you the natural and synthetic elements after we complete. So polonium is a naturally occurring radioactive element, unstable element. Then comes the halogens: fluorine, chlorine, bromine, iodine, and astatine. From polonium onwards, all the elements are, radioactive. Then the noble gases. Helium is already done. We are left with neon, argon, krypton, xenon, and radon, and that is radioactive. Of course, below astatine, you have tennessine, which has nothing to do with us, and this is organosone, which also has no meaning. It's a very, very short-lived, synthetic, and radioactive. You don't bother. Now, if you come to the middle portion to see the transition elements, these are mostly studied in terms of rows, not in terms of group. Yes, of course, both in terms of rows and also in terms of columns, groups. But first, let us take the first row, that is called the first transition series. This is called the first transition series. So it is better studied first in terms of series, then automatically group will come. So it starts from scandium, then titanium. Titanium is a very, very interesting light metal, very strong. And the frame that I'm using, this metal that I'm using in my glass, is made up of titanium. This is very handy, very strong, as well as very light. So titanium. And this is vanadium, chromium, manganese. You must know all these 10 first row elements very, very meticulously. Then iron, cobalt, nickel, they were in the erstwhile group 8, but now iron is in group 8, cobalt is 9, and nickel is in 10. And then our most liked copper and zinc. This is the first transition series of 10 elements. And then you need not bother. Let us now study in terms of groups, not in terms of the first row. We have studied in terms of rows. But let us now write down, without trying to memorize, yttrium, lanthanum, and actinium. These other members of group 3. The other members of group 4 are titanium, then zirconium, then hafnium, and then rutherfordium. This is where the synthetic element starts. So I'll be putting the synthetic elements inside a square, and those are all radioactive. So star mark is for radioactive. Then vanadium family is niobium, tantalum, Ta, tantalum, and this dubnium is nothing, is synthetic. Chromium family, chromium, then molybdenum, then tungsten. So we'll be shortly completing the periodic table, and next time, I mean in the second lecture, we'll be studying the periodic properties like ionization energy, electron affinity, the atomic and ionic size, the electronegativity, the melting point, boiling point, all these physical properties trained, how do they vary if you go across a period or you come down a group, that we will study. I'll give you the pertinent lecture notes where you can study and get it. Molybdenum, then tungsten. Molybdenum, then tungsten is W, and below tungsten is seaborgium. Let's forget about seaborgium. Then manganese, technetium, and very, very interestingly, there is one anomaly where I told you from polonium, the radioactivity starts, the instability in the element start. But here is an exception where before polonium, you find another unstable radioactive element is technetium. I'll give you the names also, the list. Technetium, and then we have rhenium, and the not interested borium, Bohr's model, that borium, it is synthetic. Then iron, ruthenium, then osmium. Then forget about hassium. Cobalt, rhodium, iridium. And forget about meitnerium, is nothing, meitnerium. And then nickel, palladium, platinum. And Darmstadtium, you simply forget, Darmstadtium. Copper, silver, gold. These three are the coinage metals in the earlier times. This was called group 1B in Roman, and these are commonly called the coinage metals because the coins were prepared from these metals. Nowadays, nobody is using gold in making coins. I was told that the 75 rupee coin that was inaugurated yesterday to commemorate the 75th anniversary of our independence. Yesterday was the inaugural function of our new Parliament House. So on that occasion, as I was told, and I think I have seen in the news that our Prime Minister Modi inaugurated or, a 75 rupee coin, and that contains a lot of silver. May not be gold. Then below gold, there is a thankless element, rhongenium. Who discovered X-rays? Rhongenium, Rg. And then finally, zinc, cadmium, mercury. As you know, a liquid but a metal is mercury. And then below it is thankless copernicium. It's named after Copernicus. Now see, here, lanthanum is here, and its corresponding 14 elements are called lanthanides. Starts from cerium. We'll not write all these 14 and ends at lutetium. And this is actinium. I am putting a sign here, triangle sign. and this is triangle sign. So the lanthanum has 14 other friends. These are called lanthanides, along with lanthanum, commonly called lanthanoids. Similarly, actinium, I put it a star mark, not star. Star, of course, will be there. It is radioactive, but I shall give another mark, a square. So this square symbol indicates that actinium has also other 14 family members. So this is thorium. After that, you have protactinium, and our uranium is here. I am not going to write all these 14 elements, and it ends at lawrencium. Well, we have completed. The only thing we have not written other 12 lanthanoid elements and other 11 actinoid elements. Doesn't matter. You can have a look in the periodic table. You can glance at them. So what is more important is to find the atomic numbers. So atomic numbers can be generated by using the magic numbers. Hydrogen is one. Just you can use a red pen to write down their atomic numbers, which are nothing but the number of electrons present in the neutral atom or the number of protons present in their nuclei. So this is 1, this is 2, leave it. Then comes the magic rule. The magic rule starts from the second period, and for the S block, it is 8, 18, 32. So in lithium, obviously lithium is 3, then you can carry on in the same period, 3, 4, boron is 5, 6, 7, 8, 9, 10. So finish the second period counting. These are the serial number, and also they are their proton number in their nuclei. We call atomic number 3, 4, 5, 6, 7, 8, 9, 10. 9, 10. Then apply the magic numbers. Add 8 to 3, you will get 11 for sodium. Then again add 8 to 11, it is 19 potassium. Then add 18 to 19, it is 37, that is rubidium. Again add 18 to 37, it is 55 for cesium. And finally add 32 to get francium, is 87. The same thing you can do with beryllium, but since we have already found out the atomic numbers of all the elements in alkali metals, add 1 to get the adjacent alkaline earth metal. This is 12, this is 20, this is 38, this is 56, this is 88. So no need to again apply 8, 8, 18, 18, 32. Now for the P block, the magic numbers are different. It is 8, 18, 18, 32, 32. You will be finding 1 8 less and 1 32 more. 1 8 less and 1 32 more. That means when you add 8 to boron 5, it will be 13. That will give you the aluminium. Then don't continue 8, continue 18. Add 18 to 13, you will get 31 as gallium. Then again 18, this is 49 for indium. And then 32, you will get 81 for thallium. And then 32, it will be 113 for nihonium. Forget about nihonium. Once you have done that, there is no need to apply 8, 18, 18, 32, 32. Instead, you can continue your journey in a horizontal manner, 13, 14, 15, 16, 17, 18. We close it here, and at home, you do not go anywhere. You order your mom to give you a cup of hot drink or whatever little food to fill your stomachs. And not only that, you join the transition metals from the S block to P block. It is 20 here in calcium, 31 here in gallium. So you just fill 21, 22, 23 and continuously go up to 30. Similarly, this is 38. 39, 30, and it continues up to 48, and you will definitely find 49 indium is waiting for you. But in this case, you have some other thing, because lanthanum has 14 other children. So once you get 57, they will come down to lanthanoids 58, and this will end in 71. Lutetium, then back to hafnium 72, and so on up to 80. Same thing will happen in actinium 88, and actinium is 89. Immediately remember its 14 children. So thorium is 90, and this will end up in 103. Lawrencium, then come back to another podium in 104 and continue up to 112, and 113 is waiting for you. 113, then continue 114, 115, 116, 117, and 118. 119 will be falling here. There is no space. This is 118, which will be discovered very soon. It is now named as, according to the Latin naming, one is called un, again one un, and 8 is called oct, and then ium will be the suffix. Un octium has been designated as its name unless it is confirmed and a new name is given. They used to call it as un 118. I'm so sorry, ennium. I'm so sorry, 118 is already gone. Nobody is pointing out my error because I'm in a hurry. So this is 100. Oh, this is not correct. This is 119. And this name will be un, another un, then ennium. N stands for 9. Unknown ennium, or 119, is the new element which is coming. Bye for now. Bye for now. Have a cup of coffee. Have a cup of, I'm sorry, you are not eligible to drink coffee. Of course, you might be drinking, but coffee will be, I think, when you are an adult, you might think of, almost you are adult. You have a lot of mustache coming out and a lot of beard coming out if you are a male guy. Bye-bye. See you soon. And who have written 119? Yes, Arjun, you have corrected me. 119. Thank you so much. Otherwise, I would have repented, and I would have feeling very sad when I will now go and drink a cup of cold drink. Then I would have repented. So that's good. Bye-bye.